Okay, guys, in this short lecture, I want to talk about something called the uniqueness theorem and relate that to boundary conditions for solving Laplace's or Poisson's equations. And I'm not going to derive the uniqueness theorem in detail like it's derived in the book, but the bigger idea is just to give you guys the knowledge or the understanding that once you find a solution to Laplace's equation, either analytically or numerically, you really have found the solution. There's only one solution to Laplace's equation given a set of boundary conditions. So let's just talk about some general properties of a solution. Okay, and this is true in all dimensions. So what I'm about to write is true in 1D, 2D, or in 3 dimensions, okay? And some of this is review, hopefully, okay, but we'll review, and that I've said it before, maybe not super familiar, okay? But first is the idea that if I find a solution for the potential, let's just remember what equation we're trying to solve. If it's Laplace's equation, we're trying to solve this equation here, okay? So if I solve that for some v, okay, over some space, whether it be 1D or 2D or 3D, it has no local minimums or maximums, okay? If I did have that, then I'm solving Poisson's equation because that tells me that there's some charge density in the region where I'm trying to solve this equation, okay? The exception of this, of course, is except at the boundaries. So if I look at a solution, okay, the highest and lowest point should be at the boundaries. And again, this is kind of like in one dimension, it would be the idea of connecting 2 points with a straight line. In 2 and 3 dimensions, again, we're trying to connect a point the most direct way possible. So some kind of a smooth surface that connects those boundary points is going to be the solution to Laplace's equation. Okay, so that brings us to our second point is our solution. Okay, it will be smooth, which the book often just calls boring, nothing special about it, and continuous, which means there isn't any jumps, right, in the function everywhere. Okay, and I say function, but sometimes, right, you can't actually write an analytical solution. So whatever the solution is, numerical or analytical. Okay, if I want to actually look at the potential at a particular point, okay, at some point in space, so at some point, maybe an x, y, and a z, or a particular r position vector, it will be the average of surrounding points. Okay, so the fancy math way of writing that is to say that I can take a line integral, a closed line integral, or sorry, we're not going to do line integral. We're going to do a surface integral of a sphere, and we're going to multiply the potential along that sphere times our area elements, okay, and then I'm going to divide it by the total area of a sphere, and this will give me the average of the values of the potential along that sphere. That's going to be equal to the value of the potential at the center of the sphere, okay? So we talked about that in the last lecture, and then the last bit is the most important bit for this particular lecture, okay, and that's the idea that our potential is unique, okay? This is big. So that means that if you find a solution that satisfies Laplace's equation and your boundary conditions, whatever they may be, it is the solution, okay? the one and only solution. Okay, this one, number 4, is also true for Poissons, okay? These other ones are not, well, it's still pretty smooth and boring and continuous, but this one in particular and this one is not true for Poissons, because if I do have some charge density somewhere, I will get a maximum or a minimum in my potential. Okie dokie, those are some general properties. So let's think about how this relates back to our boundary conditions. Okay, if I'm going to specify a boundary condition, you guys are kind of familiar with solving differential equations now, right? First order differential equations, I need one boundary condition. In that case, we call it an initial value. If I've got a second order differential equation, I need 2 boundary conditions. If I have a third order, then I'm going to need 3 boundary conditions, okay? So it goes with the order of our solution. Laplace's equation is a second order differential equation, so I need 2 boundary conditions, and I can satisfy that in a couple of different ways. I can either know V, or I can know the rate of change of the potential normal to the boundary to find a unique or specific solution to Laplace's equation. And when we talked about solving Laplace's equation in one dimension, we gave some examples where we knew both the potential at 2 points, but I also gave an example where I knew the potential at 1 point and the slope, or in that case, it was given by the charge density. Okay, you can mix and match, as I showed. So you don't necessarily either need to know the slope or the potential. You could know the slope and the potential at a particular point. One problem, especially when you're trying to solve things numerically, is you can overprescribe, which I wouldn't worry about too much in this class. Basically, you're setting boundary conditions that cannot satisfy this for some fake scenario. Obviously, it was a real scenario. You wouldn't have boundary conditions that didn't work, but you could, if you're trying to come up with a fake problem, certainly pick boundary conditions, in particular slopes of the potential at boundaries that would not satisfy Laplace's equation. Okay, so let's think a little bit more about these boundary conditions and how they relate to some things that we've already talked about in this class. Okay, we know that near, and this is very close to a conductor, we're thinking about so close that we can kind of assume that even if it's a round conductor or something like that, we can assume that the surface is flat. We're going to draw a little surface here. Of course, on this side of our surface, the electric field is going to be equal to 0 because it is a conductor. Okay, on the other side, our electric field, it's a different color here, it's pink. If it's a charged conductor, is not going to be 0, but it will be perpendicular to the wall here. And if I drew a little Gaussian surface, okay, this is the only part where it's not 0. This is my Gaussian surface. Okay, since that's the only surface that's not 0, that tells us that our electric field has to be equal to our charge density. So if you remember sigma, this is Q per area. Okay, so that's like our enclosed charge over the area divided by epsilon naught in a direction normal to the surface. Okay, since I know that the negative gradient of the potential is equal to E, I can figure out that the rate of change of the potential in the normal direction is going to be equal to negative sigma over epsilon naught. Okay. So these are my two kind of general solutions near a conductor, okay, for the boundary conditions. I know what the electric field is, but this is important. I know here the rate of change of the potential at the boundary, the rate of change of the potential at the boundary is going to be related to the charge density of the boundary, essentially proportional to the charge density. So if I look here, thinking about these equipotential lines, they're going to change more quickly if the charge density is greater near the boundary, because that's going to imply a stronger electric field near that boundary, okay? All right, let's generalize this to near any sheet of charge. Okay, now in this case, let's say I've got a positive sheet of charge, and around this positive sheet of charge, I've got an electric field that is pointing away from it. We're going to assume it's a really long sheet of charge, so any effects near the edges won't be significant. We're right in the middle of that sheet of charge, so we're going to get a nice electric field that's perpendicular. We'll describe this sheet of charge with a charge density sigma. And again, I'm going to draw that Gaussian surface. You could do a box if you want. I just find it easier to draw a cylinder. On this side, I'm going to call the electric field E1 at the top. The electric field is going to be E2 at the bottom. And those are the only two surfaces that are going to contribute to Gauss's law, because the electric field is going to be perpendicular to the area vectors on the side of my pillbox here. So I'm only thinking about contributions to that surface integral in Gauss's law from the bottom, or from the top here and the bottom. Okay, so Gauss's law, this super important guy, is going to tell me that my electric field on the top minus my electric field, again, because now the electric field is pointed in the negative direction, minus E2A, that has to be equal to sigma over epsilon naught times A. Of course, I can cancel out the A's here, and this tells me that my electric field above minus my electric field below, again, we've already found this result, is equal to sigma over epsilon naught. Okay, that tells me something about my boundary condition, about the slope of the potential normal to my surface. I know that the slope of the potential above minus the slope of my potential below has to be equal to negative sigma over epsilon naught. All right, the last useful little bit that I know here, the last couple of things, based on what we've learned before about the boundary conditions, I know that the curl of the electric field is equal to 0. Okay, so that tells me that E parallel below must be equal to E parallel above. So those two components have to be equal in order for the curl to be 0. Okay, and then the last thing I know is that if you guys remember, we thought about having a sheet of charge and evaluating the potential along a line just above and just below that sheet of charge. If we did a line with a length of epsilon, and we thought about this particular integral, so let's call this A and B minus VB. I know that is equal to the negative of the line integral E dot dl. If I take that epsilon to 0, then dl will also go to 0. This whole side will go to 0. And that basically tells me that near a sheet of charge, the potential is continuous, which is to say, I'm kind of running out of room here, sorry. It's the same just above and just below a sheet of charge. Again, why do we care all about all this? It's telling us something about the boundary conditions near these sheets of charge that we might want to solve Laplace's equation for in order to solve for an electric field in some open area between plates of charge or something like that. Okay, so this is kind of a review, but all of this we can use when we're solving Laplace's equation.